this section is about, like I said, logarithms and exponents, and they start off by introducing exponents. That is 5.1. Right, an exponential function is where we have a base raised to some exponent, right? And the exponent here is the thing that varies in an exponential function. So this is a very different class of functions than things like x to the n. Okay, x to the n is a polynomial. The base varies, the bottom, but the exponent is fixed. Here with an exponential equation, the exponent is the thing that's changing. And the base for an exponential equation, we have sort of two options. It can be bigger than 0 or less than 1. That's an A. Right, so this value is got to be bigger than 0 and less than 1, or it can be bigger than 1. So basically, it's got to be positive, but it can't equal 1. If the base is between 0 and 1, what you get is a function that looks like this. Okay, it goes down. When the base is bigger than 1, this is a more typical exponential, you get a function or a curve that looks like this. Okay. So these are our kind of general exponential functions. And you can talk about some of the properties, they're kind of increasing, and the domains and the ranges to get a feel for those kind of two different versions of exponential functions. One of the things we notice with these exponential functions is that they are one-to-one. So each input has a single output because it's a function, but each output comes from just a single input. So it's a one-to-one function. And you may remember that one-to-one functions have inverses. So this inverse function, if you remember from a while ago, we would have looked at inverses. Can't even remember how long ago that was. Let's see, yeah, back in section 2, we looked at inverse functions. What happens with an inverse function is that the input and the output switch, right? So if this point is xy, on the inverse function, it'd be the point yx. The inputs and outputs switch when we have an inverse. And graphically, what that does is that flips the function over this line. It reflects it over this line when you switch the x and the y values. So if this is the graph of the exponential a to the x, this is the graph of its inverse. And so it's a function too, I can see that, because it's defined based off of the original. And this function needs a name because it's an inverse, and so we're going to call it the logarithm. Okay. So if this is f, then this is f inverse. If f of x equals a to the x, then f inverse is going to be the log base a of x. Maybe we don't usually do this, but I'll put parentheses there just to kind of make it a little bit more clear, like the function is a to the something. And here the function is the log base a of something. Okay, so the inputs go in here. And the relationship here is given by the function and its inverse. And so to make that a little bit more maybe useful, what we can do is we can remember that a function and its inverse, we're going to switch the inputs and the outputs. So if y equals a to the x, then x is going to equal the log base a of y. And if you're going to remember one thing from this section, this would be it, easily. Okay. This is going to help us solve a lot of problems directly. It's going to help us change equations around so that we're able to solve them. It's really a big driver of pretty much everything that we learn in this section. And it comes directly from our idea of inverses. The logarithm is a new type of function. We are not as familiar with this function, and so it is much easier for us to define it in terms of its exponential. So this side is the exponential, and this side is the logarithmic. And we can convert back and forth using this rule. So if I give you an exponential equation like 125 equals 5 cubed, that is equivalent to the logarithmic function, and you just got to keep kind of all the parts in order here. 3 equals log base 5 of 125. A logarithm is really asking about an exponent, right? So like the exponent here is 3. The logarithm is really giving you that exponent, right? You can say it in words. It's not all that helpful, but it's the exponent that I raise the base to get this number, which is 3. Okay. So this is a sort of a prime tool for working with and connecting logarithms and exponential functions. There are kind of two special cases of logarithms. The log base 10 of x, we just write as the log. We don't put the 10 on there. Kind of like with the square root, we don't put the 2. This is called the common logarithm. It used to be used a lot with calculations. So if you see this, you know it means log base 10. The other one is called the natural logarithm, and sometimes written by hand with like a cursive ln. And this is the log base e. Right? E plays a really big role in exponents and logarithms. E is approximately 2.718. It's an irrational number like pi or the square root of 2, but we kind of can estimate it as this. So just don't think of it as anything too. It is got some great properties, but it's just a number, right? It's a number a little bit bigger than 2 and a little bit less than 3. It comes up enough, however, that we use this, right, to write that more often than we would log base e. Okay. So if you want to find some logarithms like the log base 16 of 4, so there's some problems in the homework like this. What you do is you say, okay, well, let's let that equal x. I don't know what it equals, so I'm going to call it x. And typically, I don't really love working with logarithms, so I would much prefer to change this to its equivalent exponential form. And that's usually going to be easier for me to solve. So I got to keep straight here. The base of the logarithm becomes the base of the exponent. So the base of the logarithm becomes the base of the exponent. The input to the logarithm becomes the output, the exponential, and the output here, this x, becomes the exponent. So, and this is a problem where you may be able to just see what x has to be, and that's fine. If you can see the answer there, that's great. If you don't, when you have an exponential equation like this, our strategy is to try and get the bases the same. So I can write these both with a base of 4 in this case. And once the bases are the same, the only way that happens is if the exponents are equal. Right, so x equals 1/2. And you may have seen that directly because the square root, right, is the 1/2 power. Square root of 16 is 4. So, you have to be able to solve some basic exponential equations, but it's much easier for us to think about a solution to an exponential equation than it is going to be to try and figure out a solution to this logarithmic equation here. That one's hard. I think if you haven't seen a lot of logarithms, it's hard to figure out what's being asked there. Okay, so that's an example right there of using that conversion factor. Okay. There are also a couple properties of logarithms, kind of just ways that logarithms work. And they do work a little differently than other types of expressions. If you have a logarithm of a product, remember that when you multiply two things together, you add their exponents. And so it turns out that since the logarithm is really an exponent, if you look at these two pieces separately, you're going to add the logarithms together. And we do see that with exponents, but not a lot of other things where multiplication sort of turns into addition. But that's because logarithms are really exponents. If you do division, it turns out it's almost the same thing, but again, because of exponents, dividing is really like subtracting the exponent. And if you have x to a power, you can bring that power out in front as a multiplier. So these are kind of three critical rules of logarithms. There are little proofs for them. I think I go through one of the proofs in the work posted on D2L. But otherwise, you got to kind of know them. Right? It's going to be hard to come up with those on your own. There are a couple other little facts that are sometimes helpful. The log base a of 1 is going to equal 0. And that's true for any expression. Okay, just give me 1 second here. I'll be right back. Okay, sorry about that. So, and this one you can come up with, so you don't really need to memorize this as a formula, because if I convert it to an exponential, it says a to the 0 equals 1. And that's, of course, true for any value of a. The fifth property here is really an inverse property. Because the log and the exponential are inverses, if I do them one after the other, they neutralize each other. And I'm going to get back just whatever that exponent is, that x. It can also work the other way. A to the log base a of x. Those are inverse functions. So they will undo each other. That's what an inverse does, right? The function goes one direction. The inverse moves us right back to where we started. So that's also a property of logarithms. Maybe this counts kind of as a property. If the log base a of x equals the log base a of y, this is actually just like what we saw with the exponents, with the bases being the same, the exponents have to be equal to one another. If the logarithms are the same, then the inputs have to be equal to one another. So this is a good strategy for solving equations. Okay, this fact here, because it gets rid of the logarithm. You don't love the logarithms there. This gets rid of those. Okay, so I think we covered enough there, sort of zipped through enough there to talk about these problems. So one of them is similar to this. It says the log of 2x minus 7 equals the log of 5x. Let's make that 5x plus or 2x plus 7. So in this case, what we have here, whoops, sorry, couldn't see that. This is a common logarithm, so it's log base 10, but it doesn't matter what the log is if it's the same base and equal to one another. This is exactly the statement here. So when you have this is great, and you really should like this, because this just means that 2x plus 7 has to equal 5x. And you can solve that. And we get 7/3. So does that work? Yeah. So this is one strategy for solving a logarithmic equation, and that's what's in 5.4, our logarithmic and exponential equations. If you can get the logarithms equal to each other, then you can get rid of the logarithms and solve what's left. Okay. The second question there gave us a different kind of equation. It looks, I'm going to give you one that's similar. The log base 2 of x plus the log base 2 of x plus 3 equals actually let me make that, let's try this, x plus 2 equals 3. that works. So this is very similar to number 11. It's not like the last one because there aren't just one log equal to another log. Right? That was nice, the last one. But here I've got 2 logs, but then I also have this number 3. So here I need a little bit of a different strategy. What I can do is notice when I have 2 logarithms added together, when I have 2 logarithms added together, I can write that as the logarithm of the product of those 2 things. So that's nice because I can combine these 2 logarithms into a single logarithm. And now that I have a single logarithm equal to a number, this is where I can convert this. I'm going to convert this to an exponential. I don't know exactly what's going to happen here, but I don't like the logarithm. I'm optimistic that the exponential is going to give me something better. So the exponential would be 2 cubed equals x times x plus 2. Well, 2 cubed is just 8, so this is definitely an improvement. Right, and it ends up, this is just a quadratic. And factors. So we got x equals -4 and x equals 2.
So can you please take it a little
Yes.
bit up? We can't see it. I can't see it down.
You can't see the
piece of paper.
You know, which part can't you see? Or
where you're writing right now.
okay.
Oh, good. Again.
Yeah, the x -4 and the x equals 2.
Thank you.
Now, when I try and put those solutions back in here, -4 and 2, it turns out 2 is fine, but -4 is going to generate some problems because if I try and take the log base 2 of -4, that's not in the domain of a logarithm. So the domain of a log of x equals f of x is 0 to infinity. So in fact, what that function looks like is this. It's only defined for x values that are bigger than 0. 0 doesn't work and negative numbers don't work. So if I get an answer that makes one of these things negative, that can't actually be an answer. So my only solution in this case is 2.
Minnesota.
Questions about this one?
How would I do that with like fraction? Because like the one I have is a fraction. It's like, I don't know. I don't like working with fractions.
Well, so if you have a fraction, like x over x plus 2 equals 7 or something like that, nobody likes fractions, right? So we want to get rid of the fraction. So like sometimes if this is subtraction instead of addition, then instead of getting multiplication here, you'd get division here. Mm-hmm. But anytime you have a fraction, you want to multiply both sides by x plus 2. Or whatever that denominator is to cancel the denominator.
Okay.
So that would be x equals 7, x plus 2. It's actually a little better because it's not a quadratic, right? But then you can solve that for x.
I guess I get it.
Yeah, anytime you have an equation with fractions, you want to multiply through to get rid of the fraction. That's really your goal there. Okay, I had another question. One second here.
If down here wasn't a x plus 2, let's say it was a x plus 3, so you multiply it by x plus 3 too, right?
Here?
Yeah.
Yeah, I multiply by whatever the denominator is to cancel it.
Okay, thank you.
Yep, I want to get rid of those denominators and deal with whatever equation I'm left with. Yeah, there's a question from 5.1, number 4. The function was 0.8 to the x, and they just wanted you to evaluate it at 1.4. So that's a calculator question. You know, no one knows what that is exactly, right? So just you got to figure out how to put that into your calculator. Right? Usually that's like a caret button like that, and then make sure you round it. Right? A lot of these answers you'll need to round, and you got to round it properly, or it's going to mark you wrong. So if it says to round to 3 decimal places, which this one does, you gotta make sure you're rounding correctly all the way out to that 3rd decimal place. Okay. So yeah, okay, let's look at this one. So yeah, this is a question that often gives students some trouble. So I'm glad this was asked, and so we can kind of all take a look at it together here. Yeah, okay. So this is number 8 from 5.5. We have this mid-year population of 5 countries in 2010 and the projected populations for 2020. Problem's getting a little dated apparently, right? We know what it is in 2020 now. So let's just look at this first country here. We want to find the exponential growth or decay. So exponential functions are really important to us because there are a lot of things that grow exponentially, right? And if you didn't know that before, the pandemic has taught you about exponential growth and how scary that can be if it's a bad thing, right? Like infections and infection rates. Growing exponentially gets steeper and steeper and steeper until it becomes incredibly steep. And that's, of course, what people were scared of, right? And all the measures we've taken to try and keep it from getting to this very steep point. Exponential decay happens with radioactive things and other things that are kind of going away. It gets slower and slower and slower. It never goes away completely, but it has this sort of reverse curve of exponential growth. And those models are here, right? So exponential growth and exponential decay can be modeled with these exponential functions. Decay is going to have a negative value in the exponent, and growth is going to have a positive value there in the exponent. Okay. So that's kind of just general growth and decay. You know, and exponential growth can be wonderful if you've got, you know, money in a bank account or a stock market, right? Those, well, stock markets go up and down, but bank accounts, theoretically, that is exponential growth over time as well. So we just wanted to apply to the right things. So what we need to do with these models is figure out what the A is and what the B is. Right, the T is going to be the time that we put in, and the Y is going to be the actual value of the thing that we're looking at. And they say let T equal 10 be 2010. So what that really is giving me here, this data in this chart is giving me a sort of an ordered pair, if you want. It's giving me, when the year is 10, it's 8.6. And then 10 years later, so when the year is 20, it's 7.1. So that country's population is decreasing. And the question is, what is the model for that? So let's go back here. So this is the information, and this is our model that we're looking to figure out. So if I put in this value of 10 and 8.6, it looked like this: A, E to the B times 10. 10B would have been better, right? B times 10. And if I put this information into the model, I get 7.1 equals A E to the 20T, 20B. Maybe it was better to do B times 10, right? Kept the order the same here. So those are the 2 points, and this model should go through those 2 points. So the A and the B should work for both of these. So this is really a system, actually. There's a couple different ways to solve it. I think the easiest is to divide this. So I solve for what A is, and then I put that into this equation. And it may look bad, but it's actually not bad, because these have the same base, this E. So I subtract, because this exponent is on the bottom, I subtract that from that. And so I get 7.1 equals 8.6 E to the 10B. Can divide that by 8.6. (7.1) divided by 8.6. It's a calculator question for me, at least. I saw this interesting thing on students doing work with like an abacus, and they were amazing, the calculations they could do by hand very quickly and accurately. Made me feel a bit subpar, but the calculator does get us through. 0.8256 rounded. Okay, so this now is an exponential equation that we need to solve. Now again, for those of you feeling a bit rattled here, this is 5.5. This is the last section in this whole chapter. So you may, if you're feeling like, oh, I'm not totally getting all of this, you may want to come back and revisit this after you work through the other parts of chapter 5, and it might, more parts of it will click, I'm sure, at that point. This is an exponential equation, and so I need, the easiest way for me to solve it is to rewrite it into a logarithm, actually, right? So this becomes the base of my logarithm. of this decimal, 0.8256, is going to equal 10b. So that's my conversion to a logarithm. We converted some logarithms to exponents. Here I'm converting an exponent to a logarithm. This is the natural log. And that's a number, right? So that's another calculator question. If I want to estimate that, I can just put that into my calculator. Natural log of 0.8256. Just put it into my calculator there. Equals this, negative 0.1916. It's a good policy. I'll add an extra decimal place there. It's a good policy to carry. I mean, obviously that decimal goes on forever, but it's a good policy to carry a lot of digits through and round at the very end. So it says, you know, round it to 1 decimal place for A and B to 5 decimal places. So I want to keep at least 5 decimal places. Maybe I should actually keep more there. And so keep lots of decimal places here. Then I divide that by 10. So my B value needs to be rounded to 5 decimal places, which is right there. And that is my B. I am not surprised that B is negative because this is exponential decay. This country's population is decreasing, so the B value or the exponent on our model is going to be negative. Negative 0.01916t. Now I still need to figure out what A is to finish my model, but now I can put in either one of these points to figure out what A is. Let's put in 8.6 here. So get this all on the screen for you, right? So I'm just going to start with this exponential. So right here, that's my E right there. E to the my negative. Don't actually use this calculator very much. Usually you have to be a little careful about the plus minus. But there apparently it doesn't mind using a negative as the minus. So I multiplied this number by 10 and did E to that number, and that gives me that. And then I take 8.6 divided by this number, 0.8256. I get 10.4. It says round this A to near it to 1 decimal place, so 10.4. So that's my model then. Y equals 10.4 e to the negative 0.01916t. And this number makes sense to me because my population, remember, went from 8.6 to 7.1, so it's getting smaller. So this value should be a negative. And when t equals 0, notice this whole expression is 1. So I get 10.4. So this is the value when t is 0, which is good. That is bigger than 8.6, right? Because the population is going down. So this question asks me for the exponential model, and this is what I want to find. Now, this question is a really good question. It is a little repetitive because you have to do the same thing 5 times. But once you do it once or twice, the other times will go quickly. It'll just be some number punching. And then finally, they do ask us what's the population in 2030. In 2030, t equals 30. So all I have to do there once I have my model is plug the 30 in for t, and that'll give me my population in 2030 or 2040, 50, 60, whatever number I put in there for t. It's going to give me that population. Questions on this one? I know it's a bit of a longer problem for sure. I mean, the whole thing to complete is a long problem, but even this one little section is a little bit. If you haven't done your work with exponential equations or logarithms, then there are steps here that are going to be hard for you to do until you get through those previous sections. But the big thing, I think the biggest idea here is the two values that we have create two equations. And if we substitute for the A, we're able to get an equation here that we can solve for the B. And once you have that B, you're on your way towards finishing the rest of the model. So once we have the rest of the model, the A and the B, then the other part is easy. You can just plug in any value you want for t and get out the population.
Do we have to make like a model or equation like this for every part of that question, or just?
Yeah, so for all 5 of them, you got to come up there. The numbers are going to be slightly different each time. So that's part of the reason I think, what are there? There's only, I think 10 questions, maybe 5.5. So think of that question as really like 4 questions, right? But the good thing is the numbers change each time, but the process is going to be exactly the same. And that's a really, we talk about when we did lines, if you have 2 points, you know how to find the line between them. This is the same idea, but now with an exponential. 2 points, there's one exponential curve that goes between those 2 points. And so we're able then to model or use an exponential relationship. And this is exactly what people are doing with the pandemic information, is they're saying, okay, I know how many infections there were 10 days ago, and I know how many infections there are today. And if it continues in that pace, and it's following this exponential curve, what is it going to be like in 10 days or 20 days? And if those numbers, which at certain times have been very scary, then that's where the news goes out and says, hey, we got to change the things. We can't keep going on this curve because it's going to lead to some bad outcomes. So this mathematical modeling is what people use to predict what's going to happen. And so it has some very real life applications. And the mathematics of it are exactly what we're doing here. There are some extra things they try and factor into their models. Excuse me. But, and it is true that things don't actually grow exponentially forever. you know, even the pandemic, it's like there are spots where if it just left unchecked, it would grow exponentially and would be catastrophic. But at some point, it would flatten out, right? Obviously, not everyone, you know, there's a cap on that, right? It doesn't go forever. There's a finite number of people and a finite number of susceptible people. But still, so this would be a different kind of model. This is called logistic growth, which is related to exponential, but it's a little more realistic in most situations. Not many things grow purely exponentially. So there's some constraints, right, on just size and other carrying capacity kind of things. So it's a little separate to the math, but that's what 5.5 is about, is applying some of these exponential questions back to some real problems. When you get to that problem, I would encourage you to follow through this part of it to help you on your way with that one. Okay. Let's see. Oh yeah, that's it. I had a couple people actually ask about that number 8, which was a good one. So okay. Any other questions?
Nothing so far.
Okay. I would, you know, for those of you, I would think that ideally you're through kind of, or into the first 3 sections of chapter 5. I know some of you are clearly ahead into 5.4 and 5.5, which is great. Keep that up, and you know, they have different scheduling things, but if you're only into like the first section, then you got to kind of step up the pace a little bit. I find exponents and logarithms, maybe unlike some of our other sections, are very divided. So like people, once they kind of get the handle of it, they do pretty well on the problems. Some of these application problems or things still cause people trouble, but by and large, they do well with the problems. But then there are always some people who, for whatever reason, they did not grasp it and they have a really hard time getting anywhere with the problems. So you want to make sure you're in the group that's doing most of the problems right. And a lot of that comes down to that conversion. So just as a sort of parting the log base a of x equals y, this is giving it kind of the other direction, means a to the y equals x. All right, you can go either way. We started going this way, but this one also can go this way. So the base of the logarithm is the same as the base of the exponential. Then you flip the y's, sort of the location of the y's and the x's. So whatever it takes, and you get your note sheet. So this had better be on there, and that's going to get you through a fair number of the problems. So make sure to remember that. So keep up the work, right? You've got basically a week to finish up the rest of chapter 5 and the quiz. If you get done early, certainly go ahead and start on the section 6. It's a little bit of a shorter section, so we do have a take-home work, and then we'll begin kind of reviewing for our final as well. So that section kind of carries us right up to the final exam. So after after our next section, I'll start posting a little bit of review information for the final.
I had a quick question.
Yeah.
It's regarding the final exam. Will it be on campus, or do you think it'll be over Zoom?
No, so there's not, yeah, I can't really.
As
no,
of right now, I'm thinking it's over Zoom.
Yeah, so it's going to be over Zoom like the midterm.
Okay.
Yep.
Just want to know. Thank you.
Yeah, no, maybe I last week might have said I would announce something. So thank you for that. But yeah, it's going to end up being over Zoom. There's just not, it's not quite right to try and bring people in yet. There's too much going on. So yes, you can plan for it over Zoom. It is scheduled for a particular day. I think I mentioned that in the schedule. Let me just pick that up here so I'm sure to get it correct. And like before, there'll be sort of two options. Yeah, so May 12th from either 10 to noon, or I have 12:30 to 2:30. So hopefully one of those times should work for you. The 12th is a Wednesday, right? So our normal class day. Okay.
Sounds good. Thank